Good afternoon, everyone, and welcome to our next IGLUNA project show. IGLUNA is an international student project coordinated by Space Innovation and bringing together student teams from all over the world to develop the technologies relevant for future space exploration. Our guest today is the team P05 from the Aachen. We will start by watching the video about the project, and then we will have a live Q&A session with our guest today. We are streaming live from Pilatus, and we hope that you will enjoy the video.
Hello everyone, my name is Juan Carlos Araño Romero. I'm the team leader of AIX2SPACE, the project with a technology for the production of high-performance materials from locally available resources, in this case, Lunarock. Our team is composed of engineers from all over the world, specialized in different fields. Half of the team are mechanical engineers, specialized in aerospace industry, development and design, among others. In addition, our team includes electrical, computer, simulation, and environmental engineers. The transport of payloads into space, for example, for research missions or the construction and supply of manned lunar stations, poses immense economic challenges, in addition to technologically complex tasks. With cost for payload transport of 1.1 million euros per kilogram to the lunar surface, and space projects requiring large freight volumes, weight reduction seems to be essential. However, raw materials from the Moon or Mars in the form of regolith are suitable for producing habitat-building materials and thus reducing freight costs for further missions into space. For this purpose, continuous mineral fibers, that is, basalt fibers, can be utilized in situ to produce fiber composites as well as thermal insulation, filters, and hydroponic mineral wool for plant cultivation, among other things. However, this requires a spinning machine that can be operated under space conditions. Due to the limited space available within the space elements like a rocket, the spinning technology of the system must be miniaturized. Therefore, the goal of this project is the development, design, and construction of a miniaturized spinning machine to produce mineral continuous fibers under near vacuum conditions. The system serves as a proof of concept of this in situ resource utilization spinning technology within the framework of the Moon Fiber project. Our mission is to build a miniaturized machine to produce continuous mineral fibers from lunar simulant.
For more than 300,000 years, humans have felt an urge to discover the unknown. With perseverance and inventiveness, we have reached the most inhospitable corners of this world. But that was not enough for us, was it? Not long ago, we succeeded in setting foot on our nearest neighbor. The Moon has always attracted our attention, full of great mysteries, but also of great hopes. Half a century after that, what keeps humanity from venturing into the unknown once again? Partly, it's just a matter of weight. Sending a liter of bottled water to the Moon's surface would cost us $1 million USD. So let's suppose we want to send a lunar base the size of the International Space Station. It would cost us 450 billion USD just in shipping costs. Therefore, the obvious question is, why send it all? Couldn't we just use materials available on the lunar surface? The answer is yes. The lunar surface is composed of regolith, a crust with basalt as its predominant rock type. This basalt is perfect for the production of mineral fibers with a wide range of applications due to its broad spectrum of good properties. For this reason, we, the Moon Fiber team at the RWTH Aachen University in Germany, have designed the first fully automated spinning plant for the mineral fiber production under extraterrestrial conditions. On Earth, this technology usually requires 10 meters high and different working levels for operators. Our prototype measures on its largest side only 40 centimeters and automatizes the production of mineral fibers, which has never been attempted before. The I-block is mainly made of carbon fiber reinforced materials and aluminum, which results in a weight under 17 kilograms. Within it, our technology can produce at the very least 180 kilometers of lunar fiber per hour. The modular system of the I-block allows the construction of larger systems simply by assembling them together. Thanks to its standard interface, the interaction between different I-blocks is fully ensured. Moon fibers can be used as thermal and radioactive insulation filters, textiles, composite materials for reinforced concrete, and even mineral wool for growing plants in space. Today we talk about the moon, but who knows what tomorrow may bring? Think of the places you will go.
So hello everyone, I would like to talk a little bit about our overview and what systems come into our machine. We have several parts. One is, for example, the vacuum chamber. Another is the heating system. We have additionally a mounting stand that holds the heating system. We have a winder and we have a vacuum pump. Also, we have an electrical box. So for the production of the fiber, we heat up the material that we want to melt inside the vacuum chamber, and then we are trying to catch the molten drops with the winder. The winder and the heating chamber are both connected through the mounting stand in an overall system, and this thing altogether goes into a vacuum chamber. The vacuum chamber is used to produce or reproduce, more exactly, the conditions of the moon. Then we extract the air from the vacuum chamber with the vacuum pump, and we have some interface cables that go to the electrical box where we have our Raspberry and Arduino and the controlling elements. Thank you. The mounting stand is used to hold the heating system, the winder, the part of the heating system which is the insulation, and some of the sensors together. So the mounting stand basically incorporates all the subsystems in one thing that can be put inside the vacuum chamber. The mounting stand is produced from aluminium and is held together by screws from different sizes depending on the positioning. We have some fine machining that is used to produce these parts, and the mounting stand is basically in the form of a ring with a few pillars, and at the bottom we have the positioning of the winder. At the top, where the ring is holding the insulation, we have a hole which allows the fiber to go through it to the winder and being additionally wound, of course. So it's made to be a structural to provide structural stability and to reduce vibrations. We have here and there some gummy parts that are making the system even more stable. So, as said before, after the material is melted inside the crucible, it starts dripping through the nozzle and drops through a hole in the insulation towards the winder. The winder is basically a spaghetti mechanism that catches the dropping fiber. We have some sensors that detect that, and it starts spinning. So there are different RPMs and different modes at which the winder can spin, and it rotates and creates a sort of thread around it, which is also distributed by an additional arm. So we do not have a singular thread thickness, but we want to have it distributed around the winder, the fiber that we are producing. By dropping on the winder and by being rotated, the material cools itself and creates super thin fibers. So for going more into detail about the heating system. The heating system is made out of going from the inside to the outside from a crucible that holds the material, some ceramic parts that hold the crucible, and around these ceramic parts is wound a Cantal wire, which is our resistive heating element. And then after that, on going circularly outside, we have a really good insulation. It is made out of polycrystalline wool, which can withstand and withhold great amounts of heat. Usually in these type of heating systems, we use good insulation. So by keeping the heat inside, we can achieve higher temperatures. Now the heating element, the Cantal wire, is used to drive the heating, and the methods by which the heating is actually achieved is through radiation and conduction. Now this is in the prototype. In the moon there is less conduction, so we will mostly rely on radiation. Now the Cantal wire, when it heats up, it radiates towards the crucible, and the crucible is made out of platinum rhodium, so it's metallic. It captures the heat and transfers it to the material inside, which we melt. And at the bottom of the crucible there is a small nozzle that allows the molten material to drop towards the other parts of the system.
Hello, my name is Paul Golden and I'll present to you our automation system. Our project needs full remote control over three major subsystems: the motors, the sensors, and the heating. All three are being coordinated by a mini-computer Raspberry Pi and a microcontroller Arduino Mega. In this couple, the Raspberry serves as the main board computer, communicating with the computer in the control room, sending commands and receiving measurements from the Arduino, as well as directly controlling the Maxon motors, which are able to speed up even to 10,000 rotations per minute. Arduino controls then the power output of the heating wire inside the furnace, which achieves temperatures as high as 1200 degrees Celsius, and plays the role of a measurement station. To control and oversee the system, we have developed an application in MATLAB. On start, the application creates a connection with the Raspberry and then enables the user to start the motors, set the speed, turn on the heating, and specify the desired temperature. It also displays all measured values from the sensors in the system and a real-time footage from the Raspberry camera. Most of our sensors use either I2C or SPI protocols, which are a simple but robust way for communication between several computers or microchips, and have been used across several industries for many years now. Amongst the sensors that we use are, for example, magnetometers, thermocouples, a pyrometer, a thermal camera. The measurements are gathered by the Arduino and sent in bundles to the Raspberry, which then sends them over to the computer in the control room. The speed of the motors and the temperature of the furnace are both controlled by a PWM signal, which is sent from respective controllers. PWM is a very efficient way to control power on almost any electrical device. Aside from regular tasks, the Raspberry runs on boot a program called a watchdog that runs in an endless loop and checks the system for any signs of malfunction, which provides us with security against unexpected conditions.
This is our electric box. We have the Raspberry Pi beneath the cables here, the Arduino controlling the sensors and everything in here, the motor encoders there, and the breadboard connecting all the messy wires. Then we have a separate box for the heating controller just to keep it away with its heat, and a big power supply with 750 watts at 84 volts, so that's 15.7 amps at max. And we connected it to the crucible, and now we are going to start the first test. We connected the pyrometer It's down here, and the thermal camera to detect the drop, and one thermocouple going inside the crucible, and a lot of other sensors are just lying around currently, and we will put them on the assembly later on when we have successfully achieved some tests.
Since our system is working with high temperature and high voltage, risk management is very important for both human safety as well as the reliability of our system. To monitor the process as precisely as possible, as Paul mentioned before, we have installed many sensors such as temperature and pressure sensors, and in case of an emergency you can switch off the heating system, the vacuum system and the winder instantly by pressing the emergency button.
As you know, we are aiming to produce fibers from the material which is similar to the material found on the moon. In order to achieve this target, we have systems set up, and to validate this system setup, we need to perform tests. We have successfully completed preliminary tests. For example, system connections were thoroughly checked, sensors and motors were tested successfully inside the vacuum chamber. After multiple tests and failures, we finally achieved the heating temperature, which is required to melt the fiber material. And we actually produced the fiber droplets. After further assembly and tests here in Mount Pilatus, we will present you the final product, that is fiber. Thank you.
Yes. So currently, all components of the prototype have been validated separately. Also, the complete assembly has been validated, and we have already achieved some glass drops and fibers. But due to some mishaps, some components we have not been able to validate a complete process startup for a long period. Once we have a stable process, we will perform the first validation of the same process but under vacuum conditions. We are confident that at the end of the week we will be able to carry out these validations. So thank you very much.
Fiber is a vision, and we will work on it for many years to bring crucial added value to mankind for exploration. Our ultimate goal is mankind's first production plant on the Moon or Mars. This will make it possible for the first time to directly use resources on another sensing body. This will eliminate the high cost of transporting materials from Earth. Moreover, exploration only makes sense if we supply ourselves on site and are not dependent on deliveries from Earth. Several years of development are still needed to turn this vision into reality. I'm all the more pleased that the student team shares the same vision and is working with great commitment to realize it. We have been working on this since 2015, and we will continue to work on it till 2025 and beyond, until the first production facility is on the Moon or Mars up and running. We are happy that the topic is becoming more and more relevant. With the student team from AIX2SPACE, we have gathered great committed people around us who are working on the realization.
And of course, we couldn't have made it so far without the help of our sponsors. We would like to especially thank Maxon, who not only manufactured our amazing aluminium stand that holds our system, but also supported us the whole journey and also helped us to have a beautiful stand at the exhibition. Rauschat GmbH, who manufactured our ceramic pieces that are crucial for the heating system. Also Air Concept that gave us our beautiful vacuum chamber Stiffy. Also CM Publicidad, a Spanish company that provided us with the t-shirts, and Studi-Werkstatt Aachen, who helped us to manufacture the cantile wire. Thanks also to the Dassault System, and last but not least, we would like to thank the Institut für Textiltechnik from our university. Thank you very much.
On testbed. So we have been running for a couple of hours before the prototype. Maybe if I get closer, we can see that there is a fiber here, or it's 14 micrometers diameter, so it's a little bit difficult to see, but here you can see one of the glass drops.
and it's connected to the nozzle inside of the thermal insulation and the motors. This is the result of producing glass fiber out of moon regolith simulant. And that will be all of our site. Now,
Thank you very much, Juan Carlos, for showing our visitors your system here on Pilatus. Now we have a bit of time for the Q&A session, and I see that we already have some questions in the YouTube chat. You have quite a complex system, so what were the biggest challenges?
Well, I will answer that. So far, one of the biggest challenges has been funding financing. We have been having this year a very motivated student team, but sadly due to the current situation of COVID, like there has been some problems reaching out to some companies, and yeah, not everyone was having a good time, so it was more difficult even for the founding on our university. But nevertheless, we have tried to find always a solution to all of the trouble that we have found during the project. Thank you.
Thank you very much, and it's great to see you here in Lucerne. Our next question is, your system seems to need a lot of energy. How do you plan to get enough energy to power it on the moon?
Well, we are using about 750 watts at the maximum, and we can use far less when the system is heated up, and we are testing in a vacuum, because in a vacuum we only have radiation and we have a thick isolation, so we think we're going to use much less energy, and then it might be provided by solar, which is much stronger on the moon than on Earth due to there being no atmosphere.
Thank you very much for the explanation. One question, however, how likely is it for the nozzle to get clogged? Well, who would like to answer?
Yeah, I could answer that. So that depends very strongly on the purity of the material that we are melting. So far, because we are trying with an experimental prototype, we have decided to go for e-glass, industrial e-glass, because we know how it's the behavior of this material. It's well known, there is enough research literature. But once we stepped on the using moon regolith simulant, we have to make sure that we are using a fine powder with little impurities, and we homogenize the material long enough to avoid all kind of impurities or material that didn't melt completely and could clog the nozzle. So it depends mostly on the process, as long as you do a proper process, and this is exactly what we are researching, that we want to make sure that we have a stable process, the stability of the process. It shouldn't be a problem, but of course it can always happen.
Thank you very much. I think there is a follow-up question about the nozzle. So do you have to empty the crucible completely before letting it cool down in case it gets clogged?
Yes, actually no. It's nice to have it empty, so you can start with other materials in case that we are doing testing with different material. But in our case, we are always working with the same material, and in the moon will be a similar situation. Except if you, of course, decide a different material, then you will need to completely empty it just to have the right chemical composition of the fiber as desired, of course.
And I think the next question is also follow-up about this. Speaking of the material, you said that you use glass as a base material. What is the difference between Lunarocks and glass?
Well, Lunarock, it's a rock. So, and glass, it's a different material. It's a glass is usually an amorphous material. And I'm sorry, I'm no mineralogist, so I cannot completely answer that properly. But glass, as I say, it's amorphous, and it has different thermodynamic property and thermochemical property as a rock, for example. So the thing is, you take the rock, the lunar rock, you melt it, and you have to achieve that this molten material will stay on a amorphous structure and not a crystalline structure. Otherwise, your glass the resulting material will be very brittle and won't have the good properties as glass fiber offer.
Thank you very much for the explanation. There is a question in the chat. Are there also terrestrial applications for your system?
Yes, of course. Our system can be used to melt any type of material and spin the fiber out of it. And it's widely used here on Earth. On the moon, we need it very much because of the cost to transport any material to the moon.
Maybe I will extend the question because, so the Earth application in this case are more related to the miniaturization of the spin machine. So a spinning machine usually takes around three floors buildings. It's a very human work consuming process where you always require to have someone, some human worker taking care of the fibers once they drop down, and you have to stick it to the winder. In our case, what we are trying is to have a full automation because, of course, on the moon, the time of an astronaut is very valuable and very precious, and you cannot always be expecting that there is going to be a human there taking care of that the machine is working properly and the fibers are being collected by the winder. So here we're going for a full automation, and this is not seen on the Earth industry. I think that it will have a lot of opportunities for the automatization of the glass fiber industry.
So what are the next steps for the project?
Maybe I can answer this. So thank you very much for the question. The next steps would be to finalize the prototype completely, as we are currently still building it up, and we need to, for example, I think maybe Juan Carlos already mentioned this, install the vacuum chamber. But this is just in the local and the short time. In the long time, there are other technologies that need to be developed for the usage of the fibers, and how are they going to be applied on the moon, of course. As once already mentioned, composites, fiber-reinforced composites is one of the major targets, and this project will continue to grow, and we expect some more interest of students as well as other organizations and companies. So we're looking forward to the next challenges for us. Thank you very much.
Thank you. We're also looking forward to see the continuation of the project. Going back to more technical questions, how much fiber can you spin out of one crucible?
Well, I can answer it. We calculated that out of 1 gram of moon regolith, we can spin about 2.4 kilometers of fiber of thickness of 16 micrometers.
Yes, thank you.
Great, impressive. And the follow-up question, how much fiber can you produce in one day?
Well, that depends on how long are you going to be working on the machine. So, as I say, 1 gram is 2.7 kilometers. So, as many grams as you want, and as many...
Yeah, at the desired speed we want to achieve, we are producing about 15 grams of fiber, and that's about 36 kilometers. So at 8 hours, yeah, it's a bit more.
Thank you very much for the explanations. I think there are no further questions in the chat at the moment. But we still have a little bit of time in case there is still something you would like to add about your project or about the field campaign. This is your chance.
Yeah, please go.
we are extremely motivated to go further and finally send our system working properly to the moon, where it can spin fibers and enable further exploration.
Yeah, maybe.
Yes. I want to go back a little bit to the technical question about the production of the fiber on the moon. So we're also limited by the amount of energy we produce on the moon and how much we can use that energy for the actual production of the fiber. So we are not going to be running here is 24/7, but on the moon is a little bit different. And it depends on the energy sources that we gather, how are they utilized, and this is one of the limitations that I wanted to mention. But overall, we're really happy with the whole project so far. We have achieved a lot. We want to thank all our teammates that are not here, as well as the organization from IGLUNA, Verkehrhaus, and the Pilatus Mountain, and the whole of Lucerne. We've had a great time, and we're looking forward for the next days as we're continuing with our project. And yeah, I think it's so much to everybody. Maria, maybe you would like to say something more.
Thank you very much. You were talking about the energy and using your project on the moon, and I saw that there was just recently one more question. Have you considered other methods for generating the energy, like concentrating sunlight?
Oh, this is a great question. So yes, this is concentrating the sunlight. This is a very good idea. I think there is another really great project at the IGLUNA, our rivals, so to say, which are doing exactly that. They have already built a rover with a Fresnel lens at the front of it that does exactly that, and they're sintering sand to create structures, 3D printing. And I think there's some differences with what we are producing, and I think Juan Carlos can extend on that.
Yes, so that's true that concentrated sunlight will be possible, and we have been, we would like to go on that approach. It's very interesting. Yes, the sintering rover is actually really impressive, but it's a little bit different. Like you are sintering, you are not melting the material. So I think that it's totally doable. But so far we have already a lot on our shoulders, and I really hope that there is gonna be future students are gonna keep working on this project, and that moment they are gonna go on that approach, because I think it's gonna be a big challenge, that it's gonna make a lot of fun, that it's gonna be a sustainable way to produce glass fiber, and that's really important that we go as sustainable as possible in our future. And I think that it's a completely possible way of achieving the melting of the glass fiber.
Thank you very much. I see that there are no further questions in the YouTube chat, so it was really great to have you here today, to see your project show and to see the live demonstration from your testbed on Pilatus. Thank you for the viewers for being with us here today. We're streaming live from Pilatus, and we hope that you enjoyed the show. Have a nice day and goodbye.